There's a space telescope quietly building the largest map of the universe ever attempted, and its first real results are already forcing scientists to rethink how fast the cosmos actually came together. This isn't Hubble. It isn't James Webb. This is Euclid, and what it's found in its opening months of operation is genuinely reshaping cosmology. Stick around, because the real story here doesn't need any exaggeration. Let's start with what Euclid actually is, because its mission is different from almost every telescope that came before it. The European Space Agency launched Euclid in July 2023. It sits roughly 1.5 million kilometers from Earth, at a gravitationally stable point called Lagrange Point 2, the same general neighborhood where James Webb operates. But Euclid wasn't built to zoom in on a single galaxy or nebula in extreme detail. Its job is almost the opposite. It's built to map enormous swaths of the sky at once, with enough resolution to still make out individual galaxies clearly. That combination, wide field of view plus sharp resolution, is what makes Euclid unusual. Most telescopes have to choose one or the other. Euclid was designed to do both simultaneously. The mission's actual target isn't galaxies themselves. It's dark matter and dark energy. The two components that together are believed to make up roughly 95% of everything in the universe, while remaining almost completely invisible to direct observation. Euclid can't see dark matter directly. Nobody can. Instead, it measures something called gravitational lensing. Tiny distortions in the shapes of distant galaxies caused by the gravity of massive unseen structures sitting between them and us. By measuring those subtle distortions across millions of galaxies, scientists can effectively map where dark matter is concentrated throughout the universe, using its gravitational fingerprint instead of any light it gives off. In November 2023, Euclid released its first set of full-color science images. And even in that first batch, astronomers were already impressed by what the telescope was capable of capturing. One of the standout images showed the Perseus Cluster, a massive collection of galaxies sitting roughly 240 million light-years from Earth. It's one of the most massive structures known anywhere in the universe. That single image captured around 1,000 galaxies belonging to the Perseus Cluster itself, along with more than 100,000 additional, much more distant background galaxies visible only as faint points of light. Many of those background galaxies had never been seen before. Some of them were so far away that their light had been traveling for roughly 10 billion years just to reach Euclid's detectors. Researchers pointed out that this was the first time any telescope had captured this many Perseus Cluster galaxies in this level of detail in a single observation. That same release included several other targets. NGC 6822, a small irregular dwarf galaxy about 1.6 million light-years away, resembling the kind of chaotic, unstructured galaxies common in the early universe. It also included NGC 6397, a globular cluster, a tightly packed swarm of hundreds of thousands of stars bound together by gravity. Euclid became the only telescope capable of observing an entire globular cluster like this in one single frame, while still distinguishing individual stars within it. And there was a detailed, sweeping view of the Horsehead Nebula, a well-known star-forming region in the constellation Orion, captured with a level of detail that surprised even scientists who had studied it for years using other instruments. But the real headline discovery came a bit later, once researchers had time to properly analyze the Perseus Cluster data. In a study published in 2025, researchers went through Euclid's high-resolution imagery of that cluster and systematically searched for faint dwarf galaxies, the small, dim, easily overlooked galaxies that typically get missed by less sensitive instruments. They found roughly 1,100 dwarf galaxy candidates scattered throughout the image. Of those, more than 600 had never been cataloged before at all. That's the kind of number that matters enormously to cosmologists, and here's why. Dwarf galaxies are extremely sensitive to the gravitational influence of dark matter. Their shapes, positions, and how they cluster together act almost like tracers, revealing where unseen mass is concentrated. Finding hundreds of previously unknown dwarf galaxies hiding in a cluster astronomers thought they already understood suggests that dark matter's fingerprint is more intricate and more widespread than earlier surveys had captured. It's a genuinely useful scientific result, not because dwarf galaxies themselves are dramatic, but because they're one of the best available tools for actually mapping where the invisible mass of the universe is sitting. Beyond the Perseus Cluster, Euclid's early data has started building towards something much larger. In March 2025, the mission released a wider mosaic covering a significant portion of the southern sky, built from a large number of individual exposures stitched together. That mosaic alone contained millions of stars and galaxies. And here's the part that puts the scale of this mission into perspective. That entire mosaic represented only about 1% of the total sky area Euclid is expected to eventually cover over the course of its full survey. Euclid's ultimate goal is to map roughly a third of the entire sky, cataloging an estimated 2 billion galaxies in 3 dimensions, creating what's been described as the most detailed 3D map of the universe ever attempted. That's the actual scale of what this telescope is building toward. Not a single striking photo, but an enormous systematic dataset spanning billions of galaxies across most of cosmic history. One of the genuinely significant findings emerging from Euclid's early data concerns how quickly cosmic structure appears to have formed. Because Euclid can observe galaxies at vastly different distances in the same image, some relatively close, some more than 10 billion light-years away, scientists can effectively look back in time by comparing them directly. Nearby galaxies show us the universe as it looks today. The most distant ones show us light that left its source when the universe was still extremely young, sometimes barely a couple billion years old. Combining those observations lets researchers trace how galaxy clusters, filaments, and large-scale cosmic structure actually formed over roughly the last 10 billion years of cosmic history. Some early analysis of this data suggests that large-scale structure may have organized itself earlier and more efficiently than existing models predicted. Dark matter appears to have clumped together and pulled galaxies into clusters faster than some standard cosmological models expected. If that pattern holds up as more data comes in, it could mean current models of how the early universe evolved need meaningful revision. That's a real, ongoing scientific question, not a settled conclusion, and it's exactly the kind of thing Euclid was built to help answer. It's also worth talking about the structure Euclid is helping to map in more detail, something cosmologists call the cosmic web. Galaxies in the universe aren't scattered randomly. They're arranged along enormous filament-like structures stretching across hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters like Perseus form. This isn't a new theoretical idea. Scientists have modeled and partially observed this structure for decades using other surveys. But Euclid's combination of wide field of view and high resolution is letting researchers trace that web with far more precision and detail than earlier instruments allowed. Between those filaments sit enormous cosmic voids, vast regions of space with far fewer galaxies than average. Those voids aren't empty in the sense of containing nothing at all, but they are shaped by the same underlying distribution of matter, visible and dark, that builds the denser structures around them. Mapping both the dense filaments and the sparse voids together is part of how Euclid will eventually help refine models of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe as a whole. By tracking the positions and distances of billions of galaxies over its full mission, Euclid can measure how the rate of cosmic expansion has changed over billions of years. Small deviations from what current models predict could point toward dark energy behaving differently than scientists currently assume, rather than staying perfectly constant over time. None of that is confirmed yet. It's an active area of ongoing analysis, and Euclid's team has been careful to describe early results as promising leads rather than settled findings. That caution matters because Euclid's full survey is genuinely just getting started. The mission is expected to run for roughly 6 years total, continuously scanning the sky and adding to its dataset the entire time. Everything described here, the Perseus Cluster dwarf galaxies, the early sky mosaic, the hints about faster-than-expected structure formation, commies from a small fraction of the data Euclid will eventually collect. As that dataset grows into the billions of galaxies it's designed to catalog, researchers expect the statistical power of the survey to increase enormously, letting them test dark matter and dark energy models with a level of precision that simply hasn't been possible before. It's also worth being upfront about something. A wave of online content has framed Euclid's early images as unsettling, ominous, even frightening, treating the scale of dark matter and the size of the cosmic web as something almost threatening. The actual science here isn't menacing. It's genuinely remarkable, in the sense that it represents real progress on one of the biggest open questions in physics. What makes up the vast majority of the universe's mass and energy? when we still can't directly detect or explain either dark matter or dark energy. That's not a reason for alarm. It's the reason thousands of scientists have spent decades building a telescope specifically designed to chip away at that question, one carefully measured galaxy at a time. So here's where things actually stand. Euclid has completed a small portion of its planned survey, released several genuinely striking and scientifically valuable images, helped identify hundreds of previously unknown dwarf galaxies in a single cluster, and started producing early hints about how quickly cosmic structure may have formed in the universe's first few billion years. The vast majority of its work is still ahead. Years of continued observation, covering a third of the entire sky, cataloging an estimated 2 billion galaxies, building toward the most detailed three-dimensional map of the universe ever assembled. That's the actual story behind Euclid's first images. Not something designed to be frightening, but something designed to answer one of the deepest, most legitimate mysteries in modern physics, using real telescopes, real data, and years of patient, systematic observation. The mission's long-term importance extends well beyond producing spectacular images that capture public attention for a few news cycles. Every observation Euclid collects becomes another carefully measured point in an enormous cosmic map stretching across billions of light years. That map isn't simply showing where galaxies happen to be scattered throughout the observable universe today. It also preserves the history of how those galaxies gradually gathered together under gravity over billions of years. By comparing nearby galaxies with those much farther away, astronomers effectively look backward through cosmic history itself. Because light requires time to travel, greater distances also mean observing the universe as it existed much earlier. Other times they reveal subtle differences that eventually lead researchers toward entirely new explanations of nature. History shows that many revolutionary discoveries began with surprisingly small disagreements between predictions and carefully collected observational measurements. Euclid has the sensitivity needed to detect exactly those kinds of subtle differences if they truly exist. Another important aspect of the mission involves gravitational lensing, one of Einstein's most remarkable predictions about gravity. Massive galaxies and galaxy clusters slightly bend the path of light traveling through space behind them. That bending subtly distorts the appearance of much more distant galaxies, located farther beyond those massive foreground structures. By carefully measuring those tiny distortions across millions of galaxies, researchers can estimate where invisible dark matter must exist. Dark matter cannot currently be observed directly through emitted light, making gravitational lensing one of astronomy's strongest investigative tools. Instead of photographing dark matter itself, Euclid measures its gravitational influence on everything surrounding it across enormous cosmic distances. Repeating those measurements billions of times dramatically improves the statistical accuracy of the final scientific results. Small uncertainties affecting individual galaxies become far less significant when enormous numbers of observations are combined together carefully. That's why Euclid's survey size matters almost as much as the telescope's extraordinary imaging capabilities. The mission isn't relying upon one extraordinary galaxy or one unusual cluster to answer fundamental scientific questions. It's relying upon overwhelming numbers of independent observations collected consistently across a substantial fraction of the observable sky. That approach greatly reduces the possibility that unusual local conditions distort the overall scientific conclusions reached later. Instead, broad statistical patterns emerge naturally from enormous datasets containing billions of carefully measured astronomical objects. Processing information on that scale presents another extraordinary challenge often overlooked outside the scientific community. Every image contains countless galaxies requiring accurate identification, measurement, classification, and comparison with observations collected months apart. Specialized software performs much of that initial work before researchers carefully verify and analyze the resulting scientific catalogs. Artificial intelligence also assists with recognizing patterns too numerous for individual researchers to inspect manually. Even so, human expertise remains essential throughout every stage of scientific analysis and interpretation. Computers identify possible patterns remarkably efficiently, but scientists determine whether those patterns genuinely represent meaningful physical discoveries. That partnership between advanced computing and careful human investigation defines much of modern observational astronomy today. The discoveries eventually emerging from Euclid will therefore reflect years of collaborative international, scientific effort rather than isolated individual breakthroughs. Researchers across many countries continue comparing results, testing alternative explanations and refining measurements before reaching confident scientific conclusions. That careful process sometimes appears slow compared with dramatic headlines appearing shortly after the first images become public. But science has always progressed through patience, repeated testing, and independent verification instead of immediate certainty. Euclid was never expected to answer every question during its first months of operation. It was designed for a mission lasting years, gradually building one of astronomy's richest datasets ever assembled. Each new observation strengthens the survey, improves statistical confidence, and expands humanity's understanding of the large-scale universe. Some of its most important discoveries may not become obvious until millions of additional galaxies have been carefully analyzed together. Others may emerge unexpectedly from patterns researchers aren't even searching for today. That possibility makes the mission especially exciting for astronomers planning research throughout the coming decade. History repeatedly shows that powerful new observatories often make their greatest discoveries completely by surprise. Euclid may ultimately follow that same remarkable tradition as its extraordinary survey continues expanding year after year. For now, its earliest results already demonstrate that the mission is performing exactly as engineers and scientists hoped. The telescope is delivering exceptionally detailed observations, while opening entirely new opportunities to investigate the universe's deepest remaining mysteries. And with most of its planned survey still lying ahead, Euclid's most important discoveries may still be waiting beyond the next observation. If you want to keep following what Euclid finds as its survey continues, subscribe and turn on notifications. The real universe keeps turning out to be remarkable enough, without anyone needing to dress it up as something scarier than it actually is.